All right, so we're going to talk about nuclear fission. So what we're going to learn, remember the subatomic particles are, describe the structure of the atom, remember the nuclear notation is, and the number which means what it means, and remember what isotopes are. You're going to watch this recording and this will help you with the CK12 nuclear fission worksheet. So why we learn the nuclear chemistry doesn't seem that important, but actually it's quite relevant today. Makes the Earth life on Earth possible. Nuclear reactions and decay are important in diagnosing and treating injury, disease, and the production of energy, atomic weapons. Nuclear decay may even be something you're looking at when you buy a new house because there might be radon in the basement. Right. So I can describe what fission is. I can explain what is needed for fission reaction to occur. I can describe what the chain reaction is, and I can describe where fission reactions occur both naturally and artificially. So we're going to be talking about isotopes. Most isotopes are naturally occurring, are stable. Remember that stability has to do with the neutrons. A few naturally occurring isotopes and all their man-made isotopes are unstable. Unstable isotopes can become stable by releasing different types of particles. This process is called radioactive decay, and elements undergo a process called radioactive isotopes, radionuclides. All right, so let's take a look and remind yourself what an isotope is. So in the atomic mass, this is the element, carbon 12. We write this way to identify this as an isotope. The atomic mass is here. That's what this means, the 12. That's the protons plus the neutrons. Neutrons, remember, have zero charge. This has a plus charge. This is the atomic number or number of protons. So let's go ahead and write carbon 14. The C for the element, hyphen, and the 14 is the atomic mass. So the atomic mass goes here, and the number of protons are there, 6. They're both, because they have 6 protons, they're both carbon. The only thing different is the number of neutrons. The protons are the same. If you add another proton to a carbon, make it go up to 7, and that would be nitrogen. So remember we said before that adding that the protons are the identification, tells what it is. So radioactive decay is a spontaneous disintegration. Right? A nucleus that's slightly, the nucleus into slightly lighter nucleus accompanied by emission of a particle. So there's a particle that's been emitted, some radiation or electromagnetic radiation, or both. So it could be both. There's 3 flavors: alpha particle, beta particle is a negative particle, gamma is a ray, goes through almost everything, and alpha particles can be stopped by a piece of paper. Alpha particles are bigger. So radioactivity is a process whereby unstable nuclei release energetic substances. Here's an animation of the decay of uranium-238. So the red are the protons, the yellow are the neutrons. Notice that other particles are being emitted, like green for gamma rays, and this has a proton and two neutrons attached to it. So notice what's happening here as we go through this. The atomic mass is going down, and as the protons are ejected, it changes into a different element. So very different than the chemical reactions we've been talking about. So nuclear changes occur when small but measurable losses of mass, like a neutron or a proton and a neutron. The lost mass is called the mass defect. Defect means to leave, and converted to energy according to Einstein's equation, E equals mc squared, where this triangle M, which means delta, or change in, triangle means change in, change. Not writing too well on this particular slide. Change in energy, speed of light. Because the speed of light is so large, the mass converted is enormous. Chemical reactions, mass is conserved. Nuclear reactions, small amounts of mass can be converted to enormous amounts of energy. So we don't have, in chemical reactions, we have bonds forming and reforming here, and that conserves the energy, conserved the mass. Here the mass is moving, is changing, and we get energy in terms of that. So fission means to split a heavy nucleus into smaller nuclei, smaller mass numbers. So we have the splitting of a large atom, uranium, can be split into krypton and barium and 3 neutrons. So notice that we're talking about a slow neutron, 0 charge. The reason being is that if this is positively charged, here it's positively charged. If this was positive charge, it would move away. But because it's 0 charge, it can go in here, break this apart into barium and krypton. All right? Now these are called daughter nuclei. This is called the parent. So fission begins when the uranium atom gains an electron, a neutron. So here we are, we're shooting a neutron, slow neutron, into uranium-235. You gain a neutron, so the mass is bigger, starts to distort the nucleus. It splits apart into the daughters. And you've got this equation here. So 235 uranium plus a neutron, a slow neutron, broke this down into Krypton and barium plus 3 neutrons and electron and energy. Now, I'll show you on the next slide how to figure out how many neutrons we gained. Okay, so here is that equation. Now notice that we have the atomic mass of the neutron. It has 0 here because it's not an element. It's 1 atomic mass unit, 1 AMU, 0 proton, so it's not an element. It breaks it down into these daughters, and we don't know how many neutrons. So we already know we shot one, so we're going to have one at the end, but let's take a look how we figure this out. So uranium-235, and we're going to subtract the mass that we have here. 143 plus 90. So 235 minus 143 plus 90 is 233. Now we have to add this neutron here to it. So we get 236 minus 233 gives us 3 neutrons. So we have 3 neutrons as my final number of neutrons that are emitted. Now notice that this 56 and 36 come up to 92, so that's conserved. The mass here is changed. All right, so there's 3. All right, what particle collides with a fissionable nucleus in order to begin? So not everything that we hit a neutron with will break apart. Not everything will break apart. Okay, so it has to be fissionable. So that's why we use something that it's unstable, can break apart, and we're using a neutron because it's a 0 charge and can hit a proton or hit the nucleus, which is positively charged. All right, so let's try this one again. This is a different one. We have uranium-235 plus 1 gives us 236. So that's what I've added the atomic masses up on the top, 235 and 1, so 236. And then I've got cesium and rubidium, so 135. 99, so that's 235 minus 1, it's 234. 234 gives me 2. So 2 neutrons. All right, in order to initiate fission, neutrons must be moving at slow speeds, right? Slow. So that's a false answer, right? All right, so uranium can undergo the process of absorbing a neutron. 233 plus a neutron gives me 234. Breaks into the daughter particles, krypton and cesium, plus 4 neutrons. That is a fission reaction. All right, so let's take a look at this FET. So click the laser gun to shoot the nucleus. What happens to the nucleus, right? How much energy does the nucleus change? What particles are released? And what does fission mean? Did I say fusion? I'm sorry, it's fission. Right, so let's go to fission. All right, so reset. Like I need to start this over again here. Wait a second or so. More like a so. Great. So look at the chart here. We have uranium-235. What our legend shows that the gray is a neutron, red is a proton, uranium-235, and the daughter nuclei. Here is a representation of the energy where this is at. It's the total energy in this particular U-235. We're going to hit it with a neutron. Bam, notice the energy goes up from where it started, splits into two pieces and some pieces ejected. So let's try this again. So here it goes lower, hit a neutron here, moves up, it shakes back and forth. And notice we have 3 neutrons at the end. Let's try it one more time. Shakes, the energy goes up, splits, and 3 neutrons ejected. All right, so let's go to this and we'll write this in here. So laser gun shoots it. What happened? Okay, so neutron hits uranium 235, becomes uranium 236 for a second, and starts to shake. The energy goes up, energy increases, and the particles that are released when the nucleus splits are 3 neutrons that we observed. Released. And what type of decay is this? What type of decay is this? This is fission and splitting. This is what this means, to split. All right. Okay, so let's take a look at this next piece here. All right, so a nuclear chain reaction is uncontrolled nuclear fission proceeding to complete at great speed. Chain reaction released by splitting of an atom off, striking other uranium atoms. Those particles begin to split off until the reaction completes. So we do get that in the simulator. Here's a chain reaction. Now, can't get a chain reaction unless we add some more particles here. So again, you need to get the certain amount so it begins. So if I start with less, so I hit 1, okay, and I get a few. and still some left over. So let's put a bunch of these in here, 235 nuclei, fill it all up. And you'll see that one bursts into another, which splits and then hits another one, and splits and splits and splits, breaking until everything is all but a couple, right? Okay, so that's a chain reaction. So here's an example. They have a chain reaction here, showing you those. Uncontrolled nuclear fission proceeds to completion with great speed. Now, in an atomic bond, we use uranium or plutonium and relies on fission. The resulting reaction is an uncontrolled nuclear chain reaction, so it produces lots of energy all at once. Now, controlled fission is in a power plant. We have a few. We have one in Michigan. Not sure if it's going to be decommissioned or turned off. People have a lot of concerns about nuclear power these days. Not as much as they did in the past, but we've had some accidents. All right, so let's take a look at a reactor. So we have uranium or plutonium in these stacks, and they're separated by control rods, and you can move these control rods up and down. This is a thermometer, and this is how much energy is produced, power output, energy produced. So we can fire a neutron. Now, of course, it may get this going on this side, but because it can't react with these other ones, then we don't get much of a chain reaction. So we're going to let this go about halfway, fire a neutron, start one off. Down here, try again, closer to the top maybe. All right, so you can see we're getting more and more. Now if I really bring this down and fire a neutron, I can get more reaction between the two. I can get lots of energy, but I also can slow it down by putting this in the way here. So not all of them are they'll be stopped by these graphite rods. So that's a controlled reaction. You can see it heats up water, turns a turbine, and makes electrical energy or electricity. Okay, so the advantages: less air pollution, no air pollution with nuclear products, but it's also non-renewable as well as coal. Disadvantage is it's very dangerous and takes thousands of years to decay, it's harmful. All right, so that's all we have for today.